Alrighty, so this is Unit 4 over nuclear chemistry. This matches SPS4 from the Georgia Standards of Excellence for physical science. This is nuclear chemistry, so we're looking specifically at the, nucleus of the atom. So everything that we do here, we're no longer working with electrons, we're now looking at the proton to neutron ratio. So with nuclear chemistry comes two main categories of reactions. You either have a fission reaction or you have a fusion reaction. In a fission reaction, so you see this FISS, I like to think of that, they said like an FIZZ, so fizz. Fission reactions is the splitting apart and so, for example, if we've got a big atom, and forgive my drawings here, so we've got big atom, all the protons, all the neutrons in the nucleus, in a fission reaction, it's going to split into typically a really, really tiny atom with like only a couple things in it, and then a smaller version of the bigger one, and we'll get more into that here in a minute. For a fusion reaction, if fission is the splitting apart, fusion is the coming together. So this is there we go. It is the coming together of the nuclei. So I like to think about this. If you know anyone who's ever had a spinal fusion, it's where they take and they fuse bones in the spine together because of an injury or because of something else that may have happened. But those two pieces have now become one. So to illustrate this, it would be where we've got atom A, atom B. They come together in a really big reaction to make a much bigger nucleus. Okay. So now when we look at these types of decay, we are specifically looking at just fission reactions that are taking place here. The first type of decay that we're going to talk about is an alpha decay. And in an alpha decay, the particle that is being emitted is a helium atom. So it has a mass of 4, an atomic number of 2, and then the symbol is He. This is sometimes called the alpha particle, but it comes off as a helium atom. Alpha particles can be stopped by sheets of paper, so they are very, very low energy. Okay. The next one is called a beta decay. Beta decays give off, this is called a beta particle, but you see this E, you see this -1 charge, it's an electron essentially. And so in a beta decay, the electron is given off. They can be stopped by wood, they can be stopped by plastics, they can be stopped by metal. So slightly higher energy than the alpha particle, but still it can be stopped by just common household items. And then you have gamma decay. And you may recognize gamma from gamma rays. It's not so much a particle, but a crap ton of energy is given off in this process, and it can be stopped by concrete. So this is why we've got things like concrete bunkers and whatnot for preparation of gamma radiation. So these are extremely high energy particles. Alrighty, so now we're moving on to half-life. So in nuclear chemistry, as stuff decays, it decays typically in the form of half-life. And so what we'll do is, we've got this little chart here that's just kind of a key to half-lives, and then we'll look at it in a graph form here in a second. So let's just start here. Number of half-lives, we start with 0, 1, 2, 3, and 4, and let's look at what happens here. So if we've no half-lives have passed, that means we've got a fraction of 1. We've got 100% of our sample remaining. Okay. If any of you like pie, we've got the holidays coming up. I like to think of this in terms of a nice pie. So we've got the whole pie right there. Okay. No half-lives, whole pie just came out of the oven. Okay, so now if one half-life takes place, there's a half that is left, also known as 50%. So when we start looking in terms of pie, in my house, Dad is the head of the household, so therefore Dad now gets half of the pie, meaning that Dad is over there enjoying his monster slice, and the rest of us are staring and drooling over the half that is remaining. 2 half-lives take place, meaning that now our half is divided by 2, leaving us with a quarter, also known as 25% of said pie. So that means my mother is next in line. She gets half of what's there. Okay, so now there is a quarter of our pie remaining. I'm the oldest of the 3. Ha ha ha. So half of the quarter means an eighth, also known as 12.5%, which means that I get an eighth of this pie. Okay, so now there's an eighth remaining. In my house, there's 2 more siblings. We don't have line 5, so I guess my brother's out of luck. But for my sister, half of an eighth is a 16th, or 6.25%, which means that she gets a nice little tiny sliver of pie. If this chart is confusing for you, you could think of it in this term. So I'm going to take a moment and draw a quick half-life graph. Okay, and now when we're looking at a half-life graph, make sure that your title is indicating what it is. So this is half-life. This tends to be, in this case, I'm going to do percent remaining. Oh, I goofed that up. Just kidding. So this is going to be a measure of time. My bad. Measure of time. And this, we're going to do this as a percent remaining. Okay. So start with 100. So that would mean 50 would be right about there. 25 right about there. 0 down here. Yes. So if we take and draw a line on this half-life graph, we start with 100, and half-life is kind of this exponential decay. The idea is that it will get smaller and smaller and smaller and smaller, but you never actually quite approach 0. And so here at 100, we would be able to, I'm going to make this smaller, we'd be able to track down and see exactly how much time, so 50 would be right about there. We would know exactly how much time has elapsed. Here's 25 about there-ish. You get the idea, and the graph that you see on your test will be much neater than that. But pay special attention to your time and to what your y-axis is when you go to look at a half-life graph. It's just supposed to help you understand the amount of time it takes for a substance to divide by half. Alrighty, so that leaves us with some pros and cons of nuclear energy, and I'm not going to try and to write these in there, but some pros are it is a really efficient energy source. It's something that does not necessarily generate a whole lot of immediate damaging waste to the environment, but the con to that is if that waste gets loose, we've got some problems. And so one of the things that they do trying to store nuclear energy, or the what comes out of the nuclear energy, is they try to take and store it in like concrete bunkers. They may sink them deep down into some pools, stick it deep underground, things like that, just to try and make sure that that nuclear energy is safe and not going to, the waste from it is not going to release out into the environment. Alrighty, so that is Unit 4 over nuclear chemistry.